after they gain access to your system. So they're not one and the same thing. Authorization and authentication, they are two completely different things. Okay, and they are part of something that we refer to as security. I don't need to define the term security. I think you guys know what you mean by security. Now, when it comes to authentication and security, one of the most fundamental principles is to never stop playing passwords in the database. This is something we never do. Okay, whatever happens, you should never, and I'm using the word never, you should never store plain passwords in the database. You should always encrypt. No, encrypt is not a good word. It's supposed to be hash. We should always hash the user's password. Not even encrypt. Maybe can encryption even encryption can also want maybe. But we should always encrypt or maybe we should always hash the user's password. Okay. Again, when it comes to authentication and security, one of the most fundamental principles is to never stop playing passwords in the database. In fact, this is very fundamental. It's a very fundamental principle to an extent that in an interview, the question will come something like, apart from never storing passwords as plain text, what are some of the other ways that you can implement security in a full stack system? That is how basic it is. So you should never store passwords in plain text. So you can imagine storing a password in plain text and then a hacker gains access to your database. Or you store your passwords as a plain text and then you accidentally push your environment variables to GitHub, and then people can now be able to access your database URL, and then they're now going to see the password of the users of that particular application. That will end up messing up everything. It will end up burning that house into to ashes. So imagine storing plain passwords and then a hacker gains access to your database. They could definitely now be able to log in as any user and do a lot of damage to your system. So the solution is that we never store passwords, we never store plain passwords, but hash versions of those passwords. That way, even if our database is hacked, the details will not be that important to the hacker. Okay, so if a user, if you're trying to log in a user, and then they give you a password like, let's say, Dennis 2025. So we don't store this password as plain text. Instead, we hash this password to get, a random garbage string like this, something like this. And this random garbage string is what is stored in the database. Now, even if our hacker, okay, not our hacker, but even if an evil person, a black hat hacker or anything in those lines, even if they came and hacked our database, these are the passwords they are going to find in the database, not the actual password. So the actual password, you never store your password as a plain password. You store a hash version of that particular password in the database. Okay. That way, even if your database ends up being hacked, they only have like a stupid version of that particular password. They can't really do anything with this. So that is very, very fundamental. Now, we're saying here that you're supposed to hash your passwords. Okay, you're supposed to hash your passwords. Now, hashing is a cryptographic function that cannot be reversed. It takes an input of random size and produces a fixed, to produce fixed size values as the output. So hashing is a cryptographic function that cannot be reversed. It takes an input of random size and produces fixed size values. So what you're trying to say here is the fact that whenever you're hashing your passwords, you should remember that okay, there are two ways to okay, what can I use as a general term? I'm not a cybersecurity expert, but you have two things here. The first thing that we have is encryption, okay, and then the second thing that we have is hashing. So when it comes to hashing, what you're trying to say is the fact that hashing cannot be reversed, which means the moment you hash your password like this, you cannot go back. Okay, with with hashing, you cannot go back. You can only hash your password into this particular hash over here, but this particular hash you cannot reverse it to get back your password. Okay, and it doesn't just apply to password; it applies to a lot of things. Now, that is what we refer to as hashing. Encryption is different. For encryption, I can hash, I can encrypt Dennis 2025 in a string that looks like maybe, this garbage string, something like that. And then I can perform a process called decryption to decrypt this string to get back my name here, or this particular password Dennis 2025. So when it comes to password, this is the one that we do. Okay, the first one, hashing. We hash our password. The moment you hash your password to get your random value, then you can never get this particular password back. And the advantage of this is that now that your password is in the database in a hashed format, even if we were to be attacked, okay, even if we were to be attacked or anything in those lines, that particular attacker cannot, they're going to have very relevant details in that particular case. So it's very yes.
So in that case,
yeah.
when the user is visiting
Yeah.
in the prompt to enter the password,
Yes.
at the enter Dennis 2025,
Yes.
it will be hashed
Yes.
and the value will be compared.
Exactly. Exactly. By the way, I think that should mark the end of this chapter. In fact, this was giving away everything. That is basically what I wanted to say. Let us just finish up what is remaining, but that is basically the process. Okay. So now that I feel like everyone is there, let me just continue. Let me just finish up explaining what it is that I was explaining. Okay. So usually we hash our password to get this particular hash over here. So I'm coming back to what the state, which is, by the way, 100% correct. I don't even want to add anything on top of that. Let me just try to explain to you guys what happens behind the scenes. Okay. So the first thing you're supposed to remember, guys, is the fact that encryption and hashing, they are two cryptographic functions. For encryption, when you encrypt your value to this garbage string, you can decrypt this particular value to get your initial data back. But for hashing is different. When you hash your password to get this garbage string, okay, then you cannot go back. And now maybe somebody was asking, if we hash our password to get this garbage string and we cannot go back, then how do I log into my application? Because the last time I created my Facebook account, I used Dennis 2025 as the password, and I'm always logging in with this one. So what Joshua has told you is 100% correct. So the next time a user comes to log in, you will also hash the same password. You will also hash the same password that the user is giving you, and then whatever value you get back, you compare it to the password. You compare it to this hash that has been stored in the database. Okay, and if the hashes are correct, then it means the user has given you a correct password. If the hashes don't match, it means that the user has given you a wrong password. So the cryptographic function that we will employ to ensure that our passwords are secure is hashing cryptographic function. Of course, we'll also use encryption today, and you guys will see the difference between encryption and hashing. But for now, the one that we're starting with is hashing. So now you guys understand the idea behind hashing. Yes?
No,
There is no, okay. I don't think there is any technology that can reverse the hash. As I've told you guys, I'm not sure I'm a security expert, but based on what I know, which could be wrong, you cannot reverse a hash. You can't reverse a hash. The moment you hash something, that's it. Yeah, it's gone like that. This is 2025. The moment you hash it, you cannot get it back. For encryption, it's easy to go back because when you encrypt something, you usually have a key with you. So with that particular key, you can apply a key to this value to get your encrypted value, and then you can apply the same key to this encrypted value to get back what is being stored in that particular encrypted text. But for hashing, we don't have anything in those lines. In fact, you guys are going to see how hashing works in a very interesting way. So for hashing, the moment you hash your item, it's gone like that. You will never see it again. If you want to perform comparisons or anything in those lines, then this particular new value that you want to perform comparison, you also hash it, and then you compare the hash values. Have I answered you? So what I was saying is that hashing is a cryptographic function cannot be reversed. We've seen that. So these fixed size values are called hash values. This one here. This is what we refer to as a hash value. Okay, so this is the hash value, and this is what is stored in the database. So this hash are called hash values, and the cryptographic function is called the hashing function. Now, hashing has a consistent and predictable nature, meaning that the same input will always produce the same hash value. same input will always produce the same hash value. Is that really true? Okay, I'm not sure about this, but we'll come back to this in a short while. Okay, so let us just come back to this. But I believe it's true. The same input will always produce the same hash value. Now hashing. Now this is where things get interesting. Hashing exhibits a certain, a very desirable effect, a very beautiful effect called the avalanche effect. It's a very, very beautiful effect in hashing. Okay, so hashing exhibits the so-called avalanche effect, which means even a slight change in the input results in drastically different hash values, ensuring high security and uncertainty. So this uncertainty here is what we're striving for whenever we're hashing our passwords. So this is what we're trying to say. In hashing, if I have a value, assuming, if I have a value like Dennis 2025, this might be hashed to something like, it might be hashed to, I don't know, I'm just trying to assume, just assuming JKL 123. And then in the future, somebody gives me a different hash, something like Dennis 2024. You can see I've only changed one item. It was Dennis 2025 and it gave me JKL 123. Now, if I pass Dennis 2024, somebody might think that, maybe to learn up doing something like JKL 1 to 2, something like that. But that is not the case, guys. Hashing exhibits a certain effect called the avalanche effect, where a slight change in the input, Dennis 2025 will give you JKL 1 to 3, but passing Dennis 2024 might give you something like this. Opening brackets, star 2025, maybe 1 to 3. This is what we refer to as the avalanche effect. A slight change in the input, just a very, very slight change in the input, results in drastically different values. It's a very, very beautiful effect according to cybersecurity experts. Okay, basically we are always striving for this effect known as the avalanche effect. A slight change in the input, a very, very slight change in the input gives you a drastically different value, that it becomes very uncertain to know where we're heading. Okay, so hashing exhibits this avalanche effect. So whenever somebody asks you about the avalanche effect in hashing, it is basically the idea that even a small change in the input gives you a drastically different value that even yourself can't imagine. A very beautiful thing. Now, hashing, the last thing, hashing employs a certain technique called salted hashing. Okay, so hashing employs this technique called salted hashing, where a unique random string called a salt is added to the input before hashing, making each hash unique even for identical inputs. Okay, so hashing employs this particular technique called salted hashing. Now, what do you mean by salted hashing? For salted hashing, we add a unique random string called a salt to the input before hashing, making each hash unique even for identical inputs. This is the reason why, guys, I was saying these two statements contradict. Same input always produce the same hash value, but this part of salted hashing, okay, when we do this practically, we will see whether that is actually the case. So for salted hashing, the reason why you end up having this avalanche effect, is because when you want to hash your password like this, Dennis 2025, okay, we're not really hashing the password itself. What happens behind the scenes is your value here, Dennis 2025, will be prefixed with a random string. So it is going to be prefixed with a random string like that one here. Okay, and then the resulting string is what will be hashed. So for you as the user, you will take the password as Dennis 2025, but behind the scenes, the hashing technology you are using is going to add this random string to the end of your password or to the end of whatever it is you're trying to hash. It doesn't have to be a password. And then the whole of this is what will end up being hashed. Now, this thing that you're adding to the very end, from this letter S all the way to, to this letter D, this is what we're referring to as the salt. This part over here, okay, this part is what we're referring to as the, okay, sorry for that. This is the part we're referring to as the salt. This part from, remember the password of the user was Dennis 2025. 2025 or whatever it is you want to hash. It is Dennis 2025. And then the hashing algorithm we are using is going to add a random string to the end of this string Dennis 2025. Now this random string is what we refer to as a salt. And this salt is what is responsible for this avalanche effect that you are seeing. Because Dennis 2025 might be given this particular salt, and then Dennis 2024 might be given this salt, a salt like that one. And therefore, this is the reason why we end up having this avalanche effect where a slight change in the input ends up giving us very completely different values. Okay, so this string we are adding is what we refer to as the salt, and the whole technique is what we refer to as the salted hashing. The salted hashing technique, we are adding a unique random string at the end of the input before hashing. Okay, and that makes each hash to be unique, even for identical inputs. So salted hashing is primarily used in password hashing. So this technique called salted hashing, it is primarily used in password hashing. And one such algorithm is an algorithm known as the decrypt algorithm. So computer science experts, these people who do PhD in computer science and they do a lot of research in computer science, they came up with an algorithm called the decrypt algorithm. And this decrypt algorithm, it employs this technique known as salted hashing. So if you want to perform this salted hashing to hash your passwords, you use this algorithm known as the decrypt algorithm. But guess what, guys? We don't have to do it from scratch. We learned about third-party packages. Okay, so somebody has already implemented it for us, and it's a very good thing because we will have to build this function on our own. And even personally, I don't even know where to start to write such a program. So in JavaScript, we have this package called decrypt.js, okay, which is it's basically a package that implements this decrypt algorithm. I remember the decrypt algorithm is an algorithm that implements this salted hashing. And what is salted hashing? Salted hashing is a hashing technique where a unique random string known as a salt is added to the input before hashing, and that makes each hash to be unique, even for identical inputs. And this salted hashing is what ends up giving this avalanche effect, a very beautiful effect when it comes to cryptography. Now the good thing is that we are a lazy generation. Okay, we're not really a lazy generation, but basically everything has been done for us. So the computer scientists have already researched an algorithm to do sorted hashing, and that is the decrypt algorithm. And in JavaScript, decrypt algorithm has already been implemented by a package known as decrypt.js. I don't know who the author is, but we have a package known as decrypt.js, which implements this sorted hashing. We have other packages such as Argon. If you look at the Argon package, it can also help you to implement this sorted hashing. Now, this is too much story. I was just wanted to show you guys how decrypt works behind the scenes. But the most important thing that you need to know is the fact that we hash our password to get this value known as a hash. Okay, we hash our password to get this value known as a hash. And as Joshua has told you, when someone is not trying to log in, okay, we ask them for the same password again, and then we still hash the same password, and we compare the hash that was stored in the database with the hash that has been produced by the algorithm of this particular input. And if they match, then we know what to do. If they don't match, we now understand hashing. And when we start talking about JSON web tokens, I'm going to talk about now encryption. You guys want to see the difference between encryption and hashing. So if you want to install the decrypt package, you run this command npm install decrypt.js, and you can see they're installing it as a production dependency. It is also going to be used in production as well as for development. Okay, so I'm going to copy that code, that installation code. So this is what we are doing before lunch. Okay, allow me to get rid of everything here. We don't need a space for now. So I'm going to run here. I'm going to run npm install decrypt install bcrypt.js. Let's enter, and this is going to install that bcrypt package. Okay, so let us now look at how we can hash a password. So hashing password using bcrypt.hash. So to hash a password, we use bcrypt.hash, and this bcrypt.hash, it takes in two parameters. The first parameter is the password to be hashed, and then the second parameter is the number of rounds the algorithm should be executed, and that is also known as the cost factor. So how many times are we applying? Okay, this cost factor usually confuses me. I've never understood what you mean by the cost factor, but the way I understood this cost factor is how many times do we want to salt? How many times do we want to salt our password? Okay, so when deciding how many rounds we want to use, we need to strike a balance, because a small number makes the algorithm faster but easier to crack, while a large number slows things down too much and can affect the performance of the application. So a cost factor between 10 and 12 is commonly recommended for most applications, and for security critical system, maybe if you're building a nuclear launcher or something, using a value of 14 or higher can be appropriate, as long as your servers can handle the extra load. Okay, so you should also consider your servers, whether they can handle too much load, because putting a very large cost factor might also end up affecting the performance of this bcrypt.hash function. So it takes in two parameters. The first parameter is the password that you want to hash, and the second parameter is the cost factor. So cost factor, according to how I understood it, is the number of times that you want to sort our password. So for example, if you say a cost factor of 10, I believe it's going to be 2 raised to power 10, and that is going to be the cost factor. The result of 2 raised to power 10 is going to be the sort factor. And this hash function, the way that this hash method, it returns a promise. So because it's returning a promise, you can use async await to consume that particular promise, or use .den and .catch to consume that particular promise. So yeah, we've installed bcrypt.js, and I'm going to import here. I'm going to import the bcrypt object from this particular bcrypt.js package. Now let us create here a function for hashing a password. So function hash password, like that. Okay, so function hash password, and we say if you want to hash a password, use this bcrypt.hash method. And it takes in two parameters. You can see the first parameter is the password that you want to hash, and then the second parameter is the salt. I think you guys know what you mean by a salt. So I can pass here a password, for example, maybe my password is going to be Dennis 2025, and then a salt of, let's say, I don't know, maybe a salt of 11 or something. So I'm using here the salt value as 11. And then this particular method is going to return a promise. So we use async and await to consume that particular promise. So async, await. And when you consume that particular promise, it returns the hash password to you. So I can say here, const hashed password. Hashed password is equal to await bcrypt.hash. And if we log to the console, this hash password, save that, and then we call our function hash password. Save this and then execute using node index.js. You will see that we get our hash password. So this is the hash password. You can see our input was Dennis 2025, and then this is the hash password. Now, guess what? Even if somebody came and hacked our database, but then this is what we will store in the database. We will not store the plain text password in the database. We'll be storing this hash password in the database. So even if somebody came and they attacked our system and they're able to hack our database, well, jokes on them, because what are you going to do with this hash over here? You can't log in with this. Okay. So now it's up to you as the user to always remember your password. That way everything works perfectly fine. Now guys, allow me to make this hash password function to receive a password. That way we at least make it usable. So this password is what you want to hash password. Let us now pass here this parameter. So Dennis 2025. And then I call the same function with the same input, Dennis 2025. So now if we execute this, node index.js, look at that, guys. Look at what is happening. Same input, then is 2025, but different outputs. But it's a good idea you guys understand what is happening behind the scenes. I've told you guys that this is sorted hashing. So sorted hashing, we are adding a random sort to these passwords over here. Okay, and that is what ends up giving us these drastically different values. You can see what the first, okay, ignore the first 1, 2, 3, 4, 5, 6. Ignore the first 7 characters. We will come back to those. But I wanted you to look from this 8th character all the way to the last one. Same thing to the next one. From the 8th character all the way to the last one. Same input and different values that you cannot even predict. A very beautiful effect that we refer to as the avalanche effect. And why is it happening? It is because behind the scenes, when you give decrypt Dennis 2025, it is going to add some random salt to it. It will add a random salt like that, and then it will now it will now hash the resulting string to give you, the actual hash on something. The next time you come back with the same Dennis 2025, it is going to add a very random salt to it. So that Dennis 2025. And then the resulting string is going to be hashed, and then you end up also getting some completely different values out here, known as the avalanche effect. Do we have any question up to that point? I want to discuss what this string looks like, because I know it's not scary for most of us here. So you can imagine if two identical outputs are producing completely different inputs. Now imagine, just imagine even changing one value to your password, even just changing one value to your password. And then guys, I don't know if you have noticed, but Bcrypt is very, very slow. You can see when I execute not init.js, look at all that time it takes, and then it gives us the value. So it is slow by design. Okay, Bcrypt has been designed to be slow like that, but we're going to discuss that later on. It has been designed to be slow like that in order to prevent against something known as brute force attacks. But we will come back to that. Otherwise, look at Dennis 2025, you can see completely different values. Okay, Dennis 2025, and then changing to Dennis 2024, it's also a very different values. And guys, I think to me this is a beautiful thing, because imagine if I'm using, let's assume you're storing plain text passwords. If my password is Dennis 2025 and Eileen's password is Dennis 2025, you can imagine how this would, be quite weird during logging in. Okay, I can't even try to imagine that, but you guys can try to see how beautiful the end up having this thing over here. So yeah, ladies and gentlemen, that is how you hash a password in Bcrypt JS. Now the hash password looks something like this. You've seen a lot of garbage characters. It looks something like that. So the first 7 characters, they represent the version of Bcrypt and the cost packet that you are using. So you can see the first 7 characters from from this $sign all the way to this $sign. The first 7 characters, they represent the version of Bcrypt. Okay, so the version of Bcrypt here, this 2B is the version of Bcrypt. And then this 11 is our cost factor. You can see our cost factor here is 11. Okay, if I was to change this cost factor to 20, which is a very bad idea by the way, 20 will make it to be extremely slow, guys, as you're going to see. But if I change the cost factor to 20, I now want you to see what will happen. Okay, that will now be very, very slow. Very bad idea actually, but anything to make you guys understand what is happening here. Actually, our machine can't even handle that. So this is the reason why I was telling you guys, you should be very careful with this number. Don't just throw values here. Are we together, guys? Are we together? Yeah, you can now imagine if this was a full stack system. You can imagine if this was a full stack system and you're using a salt factor of 20. So this is our user who has clicked login, but now at our server, we can't even finish implementing this. You can see it's like stuck or something. So as I told you guys, it is very, very important that you work with these recommended values. A cost factor of anything between 10 and 12. And then if your server can handle loads, if your server can handle high loads, or depending on the sensitivity of your application, 14 or higher can be appropriate. So in my own machine, I can't even handle a load of 20. Let me just stop this. You can see it's not even executing anymore. So let me stop that and use a different sort factor here. Maybe something like 14. 14 is going to work, but it will also be slow either way. So modulex of JS, you can see 14 is also slow. But yeah, exactly. 14, you can see after some time 14 is not working. So you can see 2B14, and that is because you're using a salt factor of 14. And when you're using a salt factor of 11, you saw the salt factor of 11 is also what is here. So that is the first 7 characters. The first 7 characters are basically the version of bcrypt and the cost factor. And then the next 22 characters after the version is now the salt, but it has been encoded. It has like been, let me just say encoded, the salt has been encoded somewhere in there. So the next 22 characters are the encoding. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20. So approximately those match characters, approximately these match characters, those 22 characters, they are the salt now, but it has been kind of encoded and some transformation done to that particular salt, and then that is now our salt. And then now the remaining characters are now your password hash. Okay, so after the first, this now should be 29 characters. After the first 29 characters, your password hash is now what comes afterwards. Okay, so your password hash is what comes afterwards. But now, collectively, all of it is what we're referring to as the hash itself. Okay, you guys have seen, okay, we are coming back to that. We can also compare hashes using the bcrypt.compare method. So now, when our users are logging in, all we do is hash the plaintext password they provide when logging in and compare that to the hash password using bcrypt.compare. So this method returns a boolean indicating whether the two hashes match. True means that those two hashes match, and false means that those two hashes, they don't match. Okay, so we use this bcrypt.compare function, which returns a boolean indicating whether the two hashes match, where true means that those two hashes match, and false means that they don't match. So let us try to do that. So what we just give me a second. Okay, back to what you were discussing. I want to create here a function. Okay, I want to create here a function which I will call compare password. So I want to call a function called compare password. So what I want to do basically is this. So if your user now is logging in, what you're supposed to do is to compare those two passwords, of which we use bcrypt dot and then you use the compare method. So bcrypt.compare, and then it takes in two parameters. The first parameter is the password that the user has given you when they're logging in. So the password, and then the second parameter is the hashed password. So hashed password. And then we can receive these two as parameters to this particular method to make it as usable as possible. So password and then hashed password. So it takes in two parameters. We're just receiving these two parameters like that. Don't worry, in our full stack apps, we won't be doing it this way. These two parameters will come from the user. But in this case, for explanation purposes, So Developent compare, and it is taking in two parameters. The first parameter is the password that we want to hash. Sorry, not to hash, but the password that the user has actually given us. And then the second parameter is the password that we can hash. Now, behind the scenes, what Developent will do is that it will hash this password that we have provided here, and then it will compare it to the hash password. If those two items match, it will return true. If they don't match, it will return false. And it does that asynchronously. So because it does that asynchronously, we know there's some promises somewhere. We're going to use async await for that. So async await. Okay, so it returns a promise. And that particular promise results to a boolean indicating whether the comparison was a success. So you can say here, const they match is equal to await, compare, and then we pass here those two values. And then when we load here, whether they match, we should be able to get a boolean indicating whether they match. So now I can call here compare password, and then I pass Dennis 2025, and then I pass here the hash password. So I'm going to pass this one here. Okay. So I'm going to pass this, and then allow me to use the same method, but now I want to work with Dennis 2024 and then pass the hash of Dennis 2025. So as we know, it's going to return true for the first one and then return false for the second one. And I want you guys to see how slow this is going to be. So when I execute this node index.js, look at the amount of time it takes. It's going to take some time before it finishes. And part of that is because of the salt factor that we are using. And guys, this slowness that you're seeing, it is intentional. The speed, the way it is slow like this, it is actually intentional. And I'm going to discuss that in the next few seconds. So you can see here we get false, false and true. So as you can see, this compare, it returns a promise that results to a boolean, and that boolean is whether the passwords actually match or whether they don't match, or whether the password and the hash, whether they match or don't match. So now here we can check. If they match, for example, we can just say something like this. If they match, just a second, if they match, you can just log to the console something like successfully logged into your account. Else, you can just log to the console. I'm just trying to do here something very simple. Wrong password. So save this, and now when we execute this, allow me to just remove this part where we are hashing them. Okay, because this is different. We already have the hashes. Here. I just want to get to see the comparison. Look at how it's taking so long to finish. So this is a lot of time it's taking to finish. And that has been done by design. So you can see for the first one, successfully logged into your account. And then for the second one, wrong password. So that is basically it about it. I hope that you guys now will get the idea behind it. Now, you guys might be asking, why is Bigfoot slow like that? So Bigfoot has been made to be slow because of something known as a brute force attack. So brute force attacks are attacks where basically the hacker, they have a list of passwords. This list of passwords is usually known as a dictionary. Okay, so your attacker, the person who's coming to attack your system, they have a list of passwords, and that particular list of passwords is also referred to as a dictionary. So what they do is that they run that particular list of passwords using a specialized software against your system. Okay, each time trying to compare whether, for example, this 2025 will work. Guys, I'm not making this up. In fact, these dictionaries are usually open source, most of them. You can literally Google something like this. I don't know why my graphics are so much misbehaving like that. You can try to Google something like this, passwords for brute force, and then you can search it on something like GitHub. And I want you guys to see what you're talking about. You can see here, for example, we have this repo. They have this list of passwords. And even you guys, you can contribute to this office. So you can put here your own passwords to help in brute force attacks. Just a second. overall maybe. Oh yeah, password is all.txt. It's a very, yeah, you can even see it's a very huge file that even GitHub cannot deal with. We can't show files that are this big right now because it contains a very huge list of passwords. Maybe I can just try to look for something that is maybe for something that is quite simple. Yeah, you can see, for example, this is a list of passwords, and this is also referred to as a dictionary. I think maybe some of you have already seen your own passwords here already. Okay, so in a brute force attack, basically what usually happens is that the attacker is going to run a list of these passwords against your login system. Okay, so each time trying this particular password, if it doesn't work, they try the next password. If it doesn't work, they try the next password until they come across a password that is going to work. Now, if Bigfoot was fast, if this Bigfoot package over here was fast, if the comparison of these hashes was fast, then brute force attacks would be very easy. But guess what? You can see how long it took for us to finish comparing one password. Okay, you can see how long it took us to finish comparing one person. Now, even this person, when they come with a very basic machine, you know, it will take them forever to even finish a list of, I don't know, maybe 200 persons or something. Okay? Plus, you know, on top of that, we can also implement something known as threat limiting to prevent these users from making too much requests. So I think you guys now get the idea. The reason why we have this, the reason why Bigfoot is slow in the first place is to prevent against brute force attacks, and this is a very important thing. So we have, you know, we have Bigfoot being extremely slow because that is how we prevent against something known as a brute force attack, and it's just great, guys. It works and it works perfectly fine.
Yeah, you talking about the first one.
Yes.
Yeah, in this,
Yeah.
can you, are we, these numbers,
Agree?
these numbers, do we find them in?
Team numbers. What do you mean by team number? Let me emphasize.
No, I mean, pin.
Yeah, I think, okay, pins, okay, I think pins are a bit different. Pins are a bit different. Again, guys, I'm not an expert when it comes to auth and sec, but I'm not sure pins will work with brute force attacks. I'm not really sure. Maybe you can go do your own research. Maybe it can work, but honestly, I'm not sure. I think actually it can work, but brute force attacks is majorly for passwords. Okay, so if somebody tries, if the way Bigfoot is slow, if they try to use this dictionary against our application, I think you'll see, for example, how just, you know, checking for these two users, you can see, look at how long it's taking. Look at how long it's taking, just, we're still waiting. And that is only two passwords. Now it's when it's bringing back a result. And it's only two of them. Okay, it's only two of them, this one and this one. So you can imagine if you're an attacker, we've implemented our system intentionally. This is the only time where we build our system to be slow. Guys, the way software engineering is very fascinating. This is the only time in software development where we want our system to be slow. This is the only time you're building, asking yourself, how can you make it even slower than that? Can you make it even slower than that? Something like that. That way, even if this guy came up with all of these passwords, I think you'll see how long it has taken us to finish authenticating two passwords. Now you can imagine all of these passwords. That person will just be discouraged, and you know, they'll just say, I'll just leave that as it is. Maybe depending on their intentions, they might be more persistent. But yeah, yes, was that a question? Joshua, are you asking something?
Yeah, I'm just thinking, hey, how do you make your own program to run slow? Do you overload the functionality?
I don't even know what they do.
Do you have, like what do you call it, interrupts, basics? What do you mean?
I think the authors of Visual.js, personally for us, we ourselves do not make it slow. But the authors of this Visual.js package, they are the ones who have made it intentionally slow. And it's a very good thing. The moment you start understanding security vulnerabilities out here, you'll come to realize it is not the silver bullet again a lot of things come together to make authentication and security to be strong, but it is one of the things that we will say actually we should try to employ that particular strategy in this system. Because, for example, if you are to make this to be very fast, if you are to make this to be very fast, then it will take this particular attacker a few seconds to brute force all of these passwords over here. Okay, it will take that particular attacker a very few seconds to brute force this particular password. But you can see the authors of this JS, they have made this to be intentionally slow. In fact, right now you can see it is on our own machine. Now you can imagine where we are making a network request. Look at up until that has not even finished yet. And now it's finishing. Now you can imagine, add this to the latency that is going to be caused by network requests. You compare that with rate limiting, it now becomes very much impossible for these users to attack us via brute force. So I don't know how they do it. Maybe they just have their own ways of doing it to make sure that the system is slow intentionally. Is there you had a question? Okay. So yeah, that is it about it. That is how you hash your passwords, and that is how you confirm your password. Now, the next thing you're supposed to do is to check password strengths. You're supposed to check your password strengths. And in the past, people were using a certain, you guys were trying to create accounts on Facebook, on Twitter, on Instagram, on any other platform, and you're being told a password should contain one letter, one number, a password should contain I don't know what and what and what. So they were doing that to also make that particular password impossible to use. Okay? You can imagine for these brute force attacks, by the way, I'm very sure one of your passwords is here because of how weak it is. So this idea of having your password to have one letter, one number, one uppercase letter, I don't know, it's so boring, guys. And it's a very, okay, even if it's a bad user experience, it's good for security, but a group of engineers from Dropbox, they sat down and they saw, this idea of having a password to have, I don't know, one letter, one number, one symbol, one this, one that. It's quite boring. Okay, so they decided, what if we score a database based on, not a database, but a password based on its strength. So if I give you a password like 1, 2, 3, 4, 5, 6, you actually look at the strength of that particular database without asking the user to give you one letter, one number, one symbol, and all of those other nonsense things. Okay? And they sat down and they started a project to basically be able to check passwords strengths. And they came up with this package called ZXCVPN. So this ZXCVPN package, it is a package used to check for strength of passwords. Okay? So this is how you use it. You call ZXCVPN. You first of all start by installing this ZXCVPN, and then we're going to use it in production. So you can see I'm not installing it as a development dependency. I'm installing it as an actual dependency. So you start by installing this ZXCVPN, and then once you install it, you call this ZXCVPN function from this ZXCVPN, and then you pass in your password. And then it's going to give you an object containing the interpretation of your results. The interpretation of your password. In fact, let us just look at that so that you see what we're talking about. I'm going to install ZXCVPN package. So give it a few seconds to install this ZXCVPN. And when that is happening, I don't want to call these functions anymore because they will make this to be so slow. In fact, I think you guys have understood what is happening here. Let me just delete everything. I think we now know how to hash passwords. So I'm going to import ZXCVPN function from this ZXCVPN package. Okay? So import ZXCVPN from ZXCVPN package. Now, what you're supposed to do is to call this ZXCVPN and you pass in your password. For example, let me assume Brian has a password. Brian, what's your girlfriend's name from that? What's your girlfriend's name?
I don't have a girlfriend currently.
You don't have a girlfriend's name. Huh?
Maybe I don't.
Come on, I told you Okay, Irene, what is the name of your boyfriend? Irene, your boyfriend's name? called? Set. City. City like this. Is that Eileen or is that Etotia? I'm always sharing about what I'm doing. Yeah, we are not using this password here. Eileen City. And then this ZXIDBN package, it will return an interpretation of this password as an object. So let us look at that particular object. We can just say here, const result is equal to ZXIDBN. So it is going to analyze this password. Let me just go to the console, CSG result. So save that, and when we execute this, non-index.js, you will see we will get an object containing an analysis of that particular password. Okay, so you can see the password is Eileen City. Now it will take approximately 305. It will take approximately 3 million guesses to get this particular password. Okay, so it will take approximately 3 million guesses to get that particular password. So 3 million guesses, I think that's a very big password. It's supposed to be a value in billions or something. Okay, it's supposed to be a value in billions or something, but it's not that bad. So Irene City, it's not that bad. You can see it will take 3 million guesses to get this particular password. That is something that is very simple for a computer to do. A computer can do 3 million guesses in, before you can even think about it. And then, okay, I don't know what to mean by this guesses from 10. What else can we look at it here? Okay, so the pattern is brute force, so it will become very easy to attack this using brute force. To attack it using a brute force attack. Token city. I'm not sure if this is the reason why the person is weak. I don't know. Okay. And it will take around 10,000 guesses to come up with this one. Okay. I don't understand what you mean by those totally. Okay. And then this is the feedback. You can see here a feedback. You can see here we have the feedback. Common names and surnames are easy to get. Look at that, guys. Very beautiful. The user might think you have AI when it's not really AI. So common names and surnames are easy to get. So you might think you're using AI, but it's ZXC with AI that has seen a pattern of a name and a surname somewhere. Okay? That is the reason why it is telling us common names and surnames are easy to get. And then it is giving you a suggestion. Add another word or two, and common ones are better. Add another one or two, and common ones are better. And then capitalization doesn't help very much. Most of us who are thinking that capitalizing is everything. And then you can see here the score is 2. So according to the documentation, a score of anything below 3 would mean the password is weak. So if the score is below 3, it means the password is weak. So you're supposed to keep asking the user to give you a different password until they go above 3. So you can say here, Irene City, we are Zuka, something like that. Irene City, we are Zuka, something like that. So if I save this, let me see what interpretation we get out of that. Running that. Yeah, look at this, guys. The score now is 4, which means that's a very, very strong password. And you can see I don't have any letters, I don't have any numbers, I don't have any symbols, I don't have, all this nonsense that they tell us. It's not supposed to be this, it's not supposed to be that. But you have a very strong password here with a score of 4.
Try to add a number in a special character.
You want me to add a number in a special character here? So a special, okay, sorry for that. A special character, maybe a number, something. And the number being 25. Save that. So for now, you can see this is what we have a score of, which is very beautiful. And according to, before I run this, according to ZXCVBN, a score of anything below 3, okay, a score of anything below 3 means that particular password is very unique. And you can see for this password here, it will take this number of guesses to crack it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It will take 18 trillion guesses to guess the password that we have. Okay, before we added this explanation to 25, it will take approximately 18 trillion guesses to guess the password that I have highlighted. Okay, and you can see for this password here, it will take this number of guesses to crack it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It will take 18 trillion guesses to guess the password that we have highlighted. Okay, it's not much better than telling the user to please give us a number, a character, a symbol, I don't know what. So let us try Joshua's approach, node index.js. And you can see, okay, I think the score goes from 0 to 4. According to ZXCVPN, the score goes from 0 all the way to 4. Okay, so a score of anything below 3 would mean it's, but now you can see Joshua, when we added an exclamation with a number, now it will take approximately 45, I think this is trillion or quintillion, if I'm not wrong. Okay, you know what, let us just try to, by the way guys, funny thing, I can't tell you numbers beyond a trillion. I don't even know what comes after a trillion. Is it a billion or billion or quintillion? Which one is it? So let us see how many guesses it will take. And this is virtually impossible for a computer to do. Okay? Maybe some sort of a quantum machine will be able to crack it using these operations, but so this is 1,000, a million, right? A billion. We are at a billion, right? Wait. Yeah, that's a billion. A trillion. After a trillion, what we go to? Are you sure? Okay, this is so embarrassing. And how many years have you been in school? For the past like 25 years, all of us here, at least you spent 20 to 25 years in school, and you don't know what comes after a trillion. Guys, we need to evaluate ourselves. We don't know what comes, even me myself, I'm not having fun with yeah, what comes after a trillion? So whatever that is, maybe it's I think it's quintillion, if I'm not wrong. But oh, it's quadrillion. So quadrillion and then quintillion. So it will take 45 quintillion guesses to guess this particular person. And I think all of us will agree, right? How will you be able to guess a person like this unless maybe you're employing some sort of social engineering? You know, if you are there is something known as social engineering, where you already know information about a person. For example, if I know the name of, if I know the name of Brian's Crash, I may be able to know that maybe. So let's say if you thought here is Brian's Crash, maybe there is somewhere his password is Zero can be taught here at 2025 or something in those lines. So that is what we mean by social engineering. But if we don't have such details, it's almost impossible to get such a password. I think we all agree, right? Is it easy to get such a password, guys? It's not easy to get such a password. And that is the reason why I agree with this ZXCVPN language. So you can check here if, so remember we have a field called score. So according to ZXCVPN, if a score is anything less than 3, then it means that particular password is a weak password. So console.log weak password. Weak password. Else, we can just go to the console.log whatever this password is. Okay, let's just say here strong password. Very simple, strong password. And now if I save this and execute it, not index.js, you will see that that password that you have used is a strong password. What if I try something like, I don't know, 1, 2, 3, 4. This is the weakest password, I think. In fact, I just want to see the result for this. But first of all, if we just execute it to see whether it's a weak password or a strong password, you can see it's a weak password. And if we load to the console the score, CLG, the result, that is. If you load to the console the result, clear this, and then execute it. If you look at the result, you will guess this password in 8 guesses. But I think we agree, right? Yeah, it will take approximately, in fact, even less than 8 guesses to come up with this 1, 2, 3, 4 password. And if you look at the suggestions, you can see we have under feedback warning. This is a top 10 common password. And then we have a suggestion, add another word or two. And the thing is that uncommon ones are better. You can literally send this as a response to the client. Okay? Look at this. We can even try to say something like this. we suggest, so see, console.log, we suggest, so if we look at the score object, sorry, if we look at this result object, you can see we have this feedback, and then we have suggestions. So we suggest console.log clg, we suggest result dot feedback dot suggestions at index 0. Maybe I just want the very first suggestion. So now, if I also want to see the warning, maybe you can also try to see the warning. Result dot feedback dot warning. Dot feedback dot warning, exactly. So now, if we try to execute this, maybe I should comment that one out. If we try to execute this, because it is a weak password, you can now imagine the user getting such a nice output. So this is a weak password, and these are top 10 common password, and then okay, maybe this is suggestion will come here. We suggest add another word or two, and a common one that's better. But let me try one of my passwords, which I know it will be very weak, but the account I don't really care about it. Dennis at 2025 star hash. So if we try to execute this one, load index.js, oh, a strong password. Really good. Let us try Dennis at 2025, which is also a login to one of my other accounts. Yep, that's a weak password. Okay, so common names and surnames are easy to guess, which is true, guys, right? I think we all agree that anyone in this class can guess one of my passwords is Dennis at 2025. Do you guys agree that? Yeah, because my name is actually this Dennis, and then you can see what they're suggesting. Add another one or two, and common ones are better. Do we have any questions up to that point? Any questions, dear friends?
So should we prevent the user from using their names in their password?
I don't know. Just bring this password to this DXCVPN, and DXCVPN doesn't know what to do after that. Because you can see I can also use my name in the password, but if I add some more characters, okay, if I add some more characters, it becomes a very strong password. You can see I will get strong password. Okay, so at the end of the day, don't be that harsh. Just make sure that the user is using a strong password. And I'm sure by the way, even this password, I think we all agree this password will be very hard to guess. By the way, I don't know how they built this DXCVPN, but it's so fascinating if you ask me, guys. And again, this is not the silver bullet to authentication and security. As I keep telling you guys, a lot of things are supposed to come together to make sure that the system is secure. Okay, these are just part. Try to look at it as these parts we are patching together to come up with a very strong authentication system. It's like building a house. Okay, when building a story building, having strong pillars is not the secret to having the strongest house. Okay, having the strongest pillars is not the secret to having the strongest house. We have a lot of other factors. The way you are mixing concrete, you and cement, whatever you want to call that, there are also factors to having a strong house. Even the security of your own home. Buying a dog and employing a watchman might not be enough. You might need to also add a CCTV. Okay, you might need to add some alarm systems. You might need to live near a police station and so on and so forth. So all of those things, they come together to ensure that we have secure systems. Do we have any questions? Any other questions? Okay, guys, now where we are heading, I want everyone to be very, very attentive. I want us to look at the concept of JSON web tokens, an extremely important topic when it comes to authentication and security. Now, for accountability, only authenticated users should be allowed to perform actions on our platform. This is very important. I think we all know this. I don't even need to explain. For instance, in a social media application like Instagram, commenting on posts, liking posts, creating new posts, deleting posts, they should be restricted to users who are logged in. And it's usually a very important thing, by the way, guys. We only want a user who is logged in to be able to perform certain actions. And I think we went through this request response cycle the other day, and we said it is very important that we always make sure that the client knows nothing about the server. Okay, don't even have to talk about all of this in DNS. Let us just have a very simple representation of the same ideology here. Okay, so this is our client. Maybe it is our laptop or something. Maybe this is our laptop. Okay, I don't know how to do a laptop. That's one. So this is maybe our laptop or something. And then this is our server. So this is our client, and then this is our server. So remember we said, guys, that only logged in users are allowed to perform actions in our applications. And at the same time, we say for performance, okay, not for performance, but for scalability of our systems, we never want to remember any details about the client. We never want to do that. And I give you guys a reason as to why we do that. It is because of something known as horizontal scaling. Okay, we not draw it here, but we might come back to that later on. So we never want the server to remember anything about our client. Which means the moment when a client makes a request to log in, the server processes that particular request to log in the client, and then it tells the client, okay, fine, you are logged in. Okay. Now, in the next request, this particular client, they want to create a post. Maybe it's we're talking about social media today in the morning. Maybe it's somebody who has been taken out and then they want to post some pictures of how beautiful their day was. So in the subsequent request, when they want to perform that particular action of posting a photo, the server is not supposed to remember whether the client is logged in or not. In fact, it's not supposed to remember anything about the client. So now here comes the question. Does that mean that, I don't even know how to put it. Does that mean that our user is supposed to log in in every request? The answer is no. So let us continue looking at this idea of JSON tokens, and we'll see how we go to these JSON tokens. So we are saying here, web applications should be designed to be stateless, meaning the server does not retain any information. For example, the user's authentication status between requests. That's what you're saying here. The server is not supposed to remember anything about the client. Nothing. The server is not supposed to remember anything about the client. Which means the next time you want to do something, well, the server doesn't remember the server doesn't even remember the login. So this means that with each subsequent request, the server does not know whether the client is authenticated or not. And this would mean that our users will have to log in with each and every request to our server, and this is a very terrible experience. Guys, you can imagine if you are using Instagram, and every time you want to like a photo, you're supposed to log in first. Which means if I see a Tochia's photo and I want to press the like button, when I press the like button, it redirects me to the login page. I log in and then I continue scrolling. If 3 seconds later I see Tibet's photo and I click on the like of Tibet's photo, it redirects me to the login page and then I log in again. Would you guys be using Instagram today? Would you be using Instagram today? No, yeah, because that's a very bad user experience. So now the developers stand down and they wonder, we don't want to store any information about the client here in the server. Okay? That is what we mean by stateless. We don't want to remember anything about the client in the server. So then how do we remember that a particular client is logged in? How do we remember that a particular client is logged in? Yes? Okay, this is just a plain representation of the client and the server. So maybe the server, the database may be somewhere here or something in the server. Come again. The server is only for storing client. The service is only for storing data. Sorry, not the server. The database is only for storing data, but the server is not supposed to remember information about the client. For example, your login status. The server is not supposed to remember any of that. there's a huge difference between storing data, okay, and remembering the information about the client. For example, remembering whether this particular person has been logged in or not. I gave you guys a very perfect explanation for this the other day, why that is the case. Let me just try to repeat that again. We said applications, for the sake of scaling and performance, applications are usually scaled horizontally like this. So we have the first server, we have the second server, and maybe they're at different parts of the world. Okay, so these are the three servers at different parts of the world. Maybe this is in US, this is in South Africa, and maybe this is in Brazil, for the sake of performance and all of those things. Okay, so these are the three different servers. Server one maybe living at Brazil, server two living at, South Africa, server three is living at US, Washington, or somewhere. Now, if a user makes a request to log into the system, or rather, if we want to perform a request response cycle, we started by asking ourselves, how do we know which server to contact? I really hope we're together to that point. How do we know which server we are supposed to contact? And we said that was the work of a load balancer. So the load balancer is the one that is taking this particular request from the client, and then it is the one that will decide which server is going to serve you. Let me just try to have this. Okay, so it will be the one that will be sending this to the server to decide which server is going to serve you, and it has various algorithms. Maybe it might pick a server that is near you, it might pick a server that is less busy, it might pick a server that is stronger than the other servers, and so on and so forth. And then it brings you back the response. Now, imagine a situation where we make the server to remember information about the client. Maybe this is server A, okay? And then this is server B, and then this is server C. So imagine a setup where we make the server to remember that the client is logged in. So if I make a login request, hey, I want to log in. So the load balancer decides to communicate with server A, hey, we want you to log in this particular person. So now server A, okay, this is the bad implementation which you're not supposed to implement, the stateful one. Okay, so server A now remembers that Dennis is logged in or Irene is logged in or something in those lines. But server B and server C doesn't have that information. Now, what if in the next request, you now want to create a post, and then that particular request gets sent to server C? Again, remember, we only want to create your post if you're logged in. But because we have implemented our applications in a bad way, because we have implemented our application poorly, server A is the only one that knows we are logged in, but server B and server C, they don't know we are logged in. So now our load balancer has sent a request to a server that doesn't know whether we are logged in or not. Are you guys seeing how weird that is? Hello guys, are we together at that point? Yeah, so you can imagine now that particular setup. This is the reason why I'm trying to say we should never store any information. Okay, there's a difference between storing data and retaining information about the client itself. So we never want to store any information about the client over here on the server. So now, what do we do if, for example, I want to create a post? Does that mean that with each request I'm supposed to log in? So let us now go back to the simple implementation. Can I answer the question? Yeah? Yeah. So let us go to this simple representation here, which we are talking about. So how is the server supposed to know we are logged in? So this means that web applications need a way to know, and I'm putting quote unquote, to know that a certain user is authenticated and authorized to perform certain actions. And there are two common ways to do this. The first way is session storage, which is what we refer to as session-based authentication. And then the second way is JSON Web Token, which is token-based authentication. So this session storage is the old way of doing whatever it is we want to do. And then JSON Web Tokens is the more modern way of doing whatever it is that we want to do. So these two strategies, they're the strategies we use to know whether the user is authenticated or whether the user is authorized to perform whatever actions it is they want to perform. So usually what happens, let us start with the first one here, which is the session storage, the old way which developers don't use nowadays. So session storage refers to a server-side mechanism that temporarily holds user information during their active session. When a user logs in successfully, the server generates a huge random string and stores the string and stores that particular string. And this string is also referred to as a session ID. And alongside it, you can store as much information as you want. The session ID is sent to the user as a cookie, and this is what the application will use to remember that the user is logged in. With all the subsequent requests, the client will have to attach this session ID via a cookie. But we're coming back to this in our explanation, or any other method it can. And then the server will take this particular session ID and query the database against it. And then the server will be able to know whether the client is authenticated or not, among other claims. So this is what basically happens. The user will make a request to login. So this is what to begin with, guys. And by the way, it's very simple. Just see how simple it was. You'll be very surprised. So to begin with, let me just try to draw our table here. So I just want you to assume that this is our database, maybe somewhere here. So this is our database. So our database is going to be made up of various columns. Maybe that is a column for the first name, that is a column for the last name, maybe the column for the password, and then an extra column for the session ID. Okay, so I'm going to have here a column for the first name, a column for the last name, and guys, I want you to be very attentive here. A column for the password. I'm just trying to come up with something here. It doesn't have to reflect the real world login scenario. And then a column for, I don't know, a column for the session ID. So this is the most important column. So now, when the user, okay, let us just try to have here some dummy users. Maybe we can try to have here, okay, sorry for that. I want some small text, maybe Jane, Jane Itotia. Maybe a password. Okay, we know the password is supposed to be hashed, but I'm just going to assume here the password is 123, and then you don't have any session ID. And then the second, maybe two more users, Irene, Tuku, and then maybe the password for Irene is ABC, and then maybe one more, Joshua, and then Gabriel, and then maybe the password for Joshua Gabriel is 4, or maybe 567, whatever that is. So now this is what happens when the client makes a request to log in. When the client makes a request to log in, maybe let's say for you to log in, we want to confirm your first name and your password. So when the client makes a request to log in, we're going to check their details, whether the details they've given us, the first name and the password, whether they actually match. So if they match, what happens is that the server is going to generate a huge random string. And that random string is also referred to as the session ID. And that session ID will be stored in the database. Maybe let's say it's Gabriel who's trying to log in. So that session ID is a very huge random string. I can just try to come up with some very dummy characters. Maybe RE 1, 2, 3, 4, 5, and then TB, something like that. I'm just coming up with something to help you guys to understand. Okay, so when a user makes a request to log in, when this particular user makes a request to log in, the server will confirm the details. And if the details are correct, the server will generate a session ID and store it alongside this user's details. And then this particular session ID will be sent to the client, and then the client will choose how they're going to store this particular session ID. Or let me just copy it. How can I copy it? So copy this, and then I want to paste it here. Somewhere here. Paste. Yeah. So that is basically what happens. So when the user makes a request to log in, when the client makes a request to log in, the server will validate the information about that particular user, and then when the login is successful, the server will generate a session ID, okay, and it will store that particular session ID in the database, and then this session ID is what gets sent to the client. Now, with all the subsequent requests, now that you have been logged in, with all the subsequent requests, let's say now you want to, I don't know, to create a post or maybe to comment on something on Instagram. When you make a request to write a comment, When you make a request to write a comment, the server will be like, hey, you know you're supposed to be logged in for me to allow you to create a comment. And the client will be like, yes, I am logged in. And then the server will be like, give me something to prove that you're actually logged in. And then the client will hand in this session ID. And then the server will be like, give me a minute. And then the server will go to the database and confirm under the session ID whether we actually have such a session ID. And if we have such a session ID, this RE12345TP, as you can see, it is matching to this user, Joshua Gabriel. Okay, it is matching to this user, Joshua Gabriel, the session ID of RE12345TP, which means actually it is true that Joshua has been logged in. So it is true that Joshua has been logged in, and even in that particular comment, we know it is Joshua Gabriel who is creating that particular comment. And then now we'll be like, yeah, you're allowed to perform that particular operation. So what if Joshua wants to log out? If Joshua wants to log out, he's going to hand over this particular session ID, and then that particular session ID will be deleted from the database. Okay, so the session ID will be deleted from the database, and that will be the equivalent of logging out. So if Joshua tries to use the same session ID, of course it is not Joshua doing it, it is the client machine doing it. If they try to use the session ID, the server will be like, give me a second, and then the server will go to the database to check under session IDs. So we have a session ID of RE12345TV. You try to look at that, it will be like, no, we can't see that. It means this particular user is not logged in. They're trying to play games with us. And then we send back a response of something like, please log in. Okay, we send back a response of something like please log in. And then when they make a request to log in, we log them in, and then we create this particular session ID. We log them in, and then we create this particular session ID. Okay, and the session ID that doesn't have to look like this. It's a huge, extremely huge random string. And then the session ID is what we send back to the client. It's like admitting somebody into your country and then you give them a passport. In fact, that is a perfect explanation. So if you come to somebody's country, you're supposed to be given a passport. If that particular passport expires or you lose that particular passport, then you don't have a right to be in that particular country. So that is the work of this session ID. When you log in here, we are giving you this passport. So it is your work to prove that you're allowed to be in this particular server using that particular passport. So, hey, I want to create a post. How do we know that you're actually logged in? You give us a session ID, and then the database confirms whether that particular session ID is a valid session ID. And if it is valid, you can see it is corresponding to a user. So we know, yeah, it is Joshua Gabriel who's trying to create a comment. And now even in the comments table, it becomes very easy. We just associate that particular comment to Joshua Gabriel, and then write their comment, whatever comment it was they were giving us. Are you guys seeing that flow? Yeah. So it is just as simple as that. And then now when Joshua decides to log out, or even we ourselves after some time, if we sense maybe let's say like 3 weeks of inactivity, we decide to make this particular session ID to expire. So the next time Joshua will come in, they'll have to log in again, and then they'll get a session ID. Now what if this is Irene, and then she tries to log in? So the server will be like, okay, you want to create a post? Yes. How do I know you are logged in? So Irene has not yet logged in. She doesn't have a session ID. Of course, it is not her Irene herself. It is her machine doing all of that. So now when she logs in, we create a random string for her, known as a session ID, and then we give it to her. Now with all the subsequent requests, she is supposed to give us that particular, somebody's whispering. She's supposed to give us a particular random string known as the session ID, and then we call it against our database to see whether actually ID has been logged in. So if we find that particular session ID in the database, then she is actually logged in. Okay, and if we don't find it, it means, well, that she is not logged in. Okay, so that is how session IDs work. And guys, please try to have a good mindset against this. They are extremely easy. I really wish you guys know how easy they work. This is a summary of how it works. The user logs in by sending their email address or username and password to the server through a request. We know that is how it usually works to start with. And then the server checks if the details match what is stored for the user. If everything is correct, the server makes a session, quote unquote session, that holds the user information, like user ID, permissions, and that information is kept safe in the server storage. And then the server sends a session ID back to the client corresponding to the created session. So whenever the client wants to do something from the server, their device automatically includes the session ID in its request. So the device will be using that particular session ID to prove that it has actually been logged in already. Okay, I've given you guys a very nice analogy of a passport. When you're a visitor, when you're a visitor when you want to visit the country for the first time, you first of all get a passport. So that passport, for as long as it is a valid passport, you'll be using it to say that I'm like a citizen of this particular country. And then if you want to leave that particular country, maybe you invalidate that particular passport or something in those lines. So it's the same thing here. When you want to log out, you make a logout request and then you delete this particular session ID. Now back to what we were talking about. Whenever the clients want something from the server, their device automatically includes this session ID in the request. And then the server will use this ID to find information about the session user stored in the session storage. I think you guys have seen that. So the server, so this particular client, they will use this particular session ID alongside each and every request. They're using this session ID alongside all the requests. Okay. And then the server will go to look at this particular session ID and see that, hey, this session ID corresponds to Joshua, meaning Joshua is logged in. And if we don't find anything that matches that particular session ID, we'll just tell them something went wrong or something of those kinds. Now, you guys have seen the problem with session storage, and this is the reason why developers decided session storage is a no. Can somebody tell me the hitch they have seen in session storage? Can you guys tell me what you have seen, a hitch you have seen with session storage? If you've not seen a problem with this session storage, it's 100% okay. Anyone? Anyone who has seen the problem with session storage? Okay. Now, the problem with session storage is the fact that whenever we make a request to the server, you can see with each request, we want to confirm that the user is logged in. And how do we confirm the user is logged in? They give us their session ID. Okay? With each request, we must confirm that the user is logged in. How do we know the user is logged in? They give us their session ID. And how do we use the session ID to confirm that the user is logged in? We make a database query. So you can now see with each request, apart from the query that will now perform the actual action, for example, you want to create a comment, you want to create a post, you want to delete a post, we have an extra database query to confirm that you're actually logged in against that particular session ID. You guys can see how bad that is. Okay? Which means for every user who wants to write one comment, we make two database queries. The first query to confirm that this particular session ID is valid and corresponds to an actual user in our database, and then the second query to actually do that particular thing we wanted to do, maybe to create a post, to update a post, or to delete a post. And that ended up increasing something known as latency. So in system design, we have something known as latency. So latency is the amount of time it would take to finish processing a request. So the latency is drastically increased here because with each and every request, we must make this extra database query to confirm the user is logged in. And apart from confirming that the user is logged in, we now have to make the other actual database query, which is to confirm or rather to perform the action that they actually wanted to do. So developers, that was one of the things why working with session storage is extremely slow. So with every request we make, there's an extra time needed to query the database against the session ID in order to prove that the user is authenticated. And this adds extra latency in our application. And what ends up happening is that our applications tend to be slower. And then on top of that, the sessions are stored in the server. You can see what is happening there, which can lead to increased memory usage as the number of users grow. So you can see we need an extra space to store this session ID, which guys, as you can see, it's so problematic. Okay. So this can lead to increased memory usage as the number of users grow, and this can become problematic in high traffic applications like Instagram, Facebook, and Netflix. So the developers were looking at these problems, and they were like, we cannot continue using session IDs. So we still have applications that use session ID for authentication and authorization, but the modern way of doing this is to use a JSON web token. So for a JSON web token, it's 100% similar to what is happening here in session storage. But now we don't have this extra step over here. We don't even have to use any database, I don't know, session ID and all of that. Okay, we don't even have to use any of this when it comes to JSON web tokens. Why? It is because JSON web tokens, they will encrypt a user's information in a string known as a JSON web token. So JSON web token is a method for representing claims between two parties, and it is completely stateless. Okay. Let me see where we are. Yeah, here's the flow. When the user is authenticated successfully, we take the data needed out of their record. Okay. Data that is important for authentication, but not that important that we don't care if it got exposed. And then we take a key, okay, and encrypt that particular data with the JWT library. I'm coming to see this in a short while. And this creates a huge string consisting of 3 parts: header, data, and signature. And this string is referred to as a token. And then that particular token is returned to the client. So with all the subsequent requests, the client will have to attach that particular token. And then when the client makes a request, the server uses the token to verify that particular user. And then it uses a secret key to verify that the token is right. Okay, we're going to look at all of that. But for now, I think the most important thing to understand is the fact that JWT is a method for representing claims between two parties, and it is completely stateless. And it is made up of 3 parts. We have the header, the data or the payload, and the signature. So it looks like this. It contains 3 parts separated by a dot. So the header contains metadata about the token, such as the type of token and the signing algorithm used. For example, this algorithm or that algorithm or that algorithm, and so on and so forth. And then the data, somebody is whispering. And then the data contains the claims. For example, the username, the role, the email, all of that is put inside of that particular token. And then the signature, this signature over here, is used to verify the authenticity of the token and ensure that the payload has not been tampered with. Okay? So JWT encryption can be symmetrical or asymmetrical. So symmetrical, by the way, this now is an encryption algorithm. We need a key for this one. This is not a hashing algorithm, it's an encryption algorithm. Okay? So for this symmetrical encryption, we use the same key to create a token and to validate that particular token, as we're going to see in a short while. And then for asymmetrical encryption, we create a token with a different key and validate that particular token using another key. Again, we're coming back to that in a short while. And then the token is returned to the client, and with all subsequent requests, the client will have to attach this token. So when the client makes a request, the server uses the token to verify the user. Okay. So when the client makes a request, the server will use that particular JSON web token to verify that particular user. And it uses the secret key that you are working with to verify that the token is right. And the key is compared against the token in the signature part, and if it is good, the flow continues. Now, what are problems with this JSON web token? A JWT token has a time period during which it is valid and can be used to authenticate the user. This is very important because you need to look at that. So a JSON web token, we are not storing it in a database. By the way, if we come back here to our session storage was cool because if somebody logged in on your behalf, it will be very simple. You can just contact support or something. Okay. So if okay, guys, there is something important with session IDs, it was a bit simpler, and that is because of this. When the client makes a request, okay, maybe the moment you realize that you have been compromised, the moment, for example, Joshua realizes that he has been compromised, they can just talk to support to tell them that, hey, my account has been hacked, and then maybe the support can actually delete this particular session ID on their behalf. So logged in using Joshua's account, they'll not be able to use that particular session ID anymore. But for JSON Web Tokens, we don't have a way of storing them in the database. Okay, they're not, in fact, they're not stored in the database. So for JSON Web Tokens, they have a time period during which they are valid and can be used to authenticate the user. And after that particular time, they become invalid and cannot be used to authenticate the user anymore. So that is what we refer to as the expiry time of a token. So if this particular token is stolen and it had a very long expiry date, there's nothing else a user you can do. Okay, because I mean, it is not being stored in the database. You know, the moment the user ends up stealing that particular token, there is nothing we can do. We just have to wait for that particular token to expire. Okay, so if it was a session, it would be easier because we would simply remove or truncate that particular session ID from our database. So a common way to deal with this particular problem is to make our tokens to have a shorter lifespan, for example, 10 minutes. This way, even if someone stole the token, they will only have a very short time with it. So we make that particular short token to have a very short expiry time. That way, even if somebody ended up selling that particular token, they only have a very short time with that particular account. However, this will force the user, okay guys, let us just pause the class at this point. We'll pick up from there tomorrow. So, are we together? By the way, today at your own time, you go through that topic of JSON Web Tokens. So go through that topic of JWT. Oh, I'm still sharing my screen. Oh my god, where did it forget it was just there? I'm sorry for that. Yes, that's what you want.
This is why South Korea feels like it's already living in the year 2030s. When someone parks in a no parking zone, officers don't waste time calling a tow truck. Instead, they roll out this tiny but powerful machine that slides right under the car, lifts it gently by the tires, and moves it away, all with remote control. No loud engines, no scratches, no traffic blockages, just pure precision and high-tech efficiency.
Temporarily tu niitwe kama ndimo niweke videos fulani.
Niangalia kama
Iko na GB ngapi?
hapana, hii imeharibika.
Ile inafanya iko wapi?
Ni ati sijakuja na imeharibika.
No loud engines, no scratches, no traffic blockages, just pure precision and high-tech efficiency. It's innovations like this that make you realize the future is already here. Hit that subscribe button for more.
Hey, you can leave. You make sure you go through your name. Today at your own time, you try to rewrite that API that we built, like the day that the assignment. Yeah, because kutoka kesho sasa kesho nyuma sasa, I don't know. So please, at your own time, you try to rewrite it without AI, without copying anyone's work. And then you also go through that topic of JSON and projects.